Yes, Madhukar, you can start. I have made you the co-host.
Okay, yeah, sure, sir. Am I audible?
Yes.
Okay, yeah.
Thank you very much.
Yeah, it's my pleasure to, of course, talk about some of these things here to this class. Sir, if I get disconnected, I'll because of some power cut or something, I'll join back immediately. But if I cannot, or if I'm not joining, then you just call me on my phone. I've kept it right.
Sure, I will. Yeah. Why, you suspect a power cut?
Yeah, it's been raining heavily.
I see. Okay, so we'll keep our fingers crossed.
Yeah,
improvise.
Yeah, okay. Sure. Thanks. So I'll.
Yeah, so I've already introduced you to the class. So
yeah, and yeah, very briefly, if you could also tell me what the class has learned so far.
Okay, so like. Yeah, I have increasingly made. Okay, so they've run starting with modeling of systems using modeling of software, hardware with transition systems. They know about transition systems, how to symbolically model them using propositional logic. Okay, so they've learned and used SAT solvers, BDDs. Okay. And they have looked at LTL, CTL star.
Okay.
Okay, and model checking, starting with bounded model checking, and how to make it complete using K induction.
Okay.
They
also looked at programs and invariants and properties.
Yeah, so that, yes. Okay, so then I cover what I call a K induction. So programs, invariants, I mean, you could refresh that. So since I've also covered, the notion of inductive invariance. Okay. And because K induction, they'll have to know, but the inductive invariance. So CTL model checking, I've covered as computing fixed points.
Okay.
After that, so they know about inductive invariance. Maybe giving a refresher could be to set up the thing should be fine. So then this time I also covered PDR. Okay, that is the ICT algorithm. They have implemented as a midterm project CTL model checker using BDDs. And as a final project, joint project between the three, they are implementing PDR. Okay.
Okay.
The PDR algorithm. Yeah. So have I missed anything, guys, from covering? Of course, then LTL model checking as a Tableau method, which is kind of what. So what I'm not covered is kind of the automata, approach, the automata framework. Okay.
The Buki automata.
Yeah, the Buki automaton I have not covered, but then the LTL model checking using Tableau method is very much like the Tableau that I have defined is the Buki automaton.
True.
But formally, I am not introduced Buki automaton and Omega regular languages. They have only known that on the site. So in that sense, they have, I've concentrated more on symbolic model checking, how to model using propositional logic and how to manipulate them using BDDs and SAT solvers, and how to implement fixed point things. And I also talked about the interpollant-based model checking method. Okay. Not the lazy abstraction. Not the lazy abstraction with the interpolants, but rather
but they know interpolation
over approximation through the thing. But I think what you should do is inductive invariance, etc. They know. What they probably don't know much about is what is abstraction. Okay, specifically what predicate abstraction.
Yeah. Certainly, so I'll certainly cover that. And yeah. So going ahead, how much of the course is remaining? And
I think this is the last class.
Oh, this is the last class, is it?
So whatever that you cover,
Okay.
is it. So so they will.
Oh, okay.
This will be like
Yeah, sure. Yeah,
maybe
thanks a lot.
icing on the cake.
Yeah, yeah, I hope so. Yeah, thanks a lot, sir. Yeah, so that really helps. And yeah, so so this is not a very good.
So I have already put you on live stream, but I will start recording too.
Yeah. So are these slides visible if I keep them like this?
Yes. Yeah.
Okay. Yeah. Thanks. This allows me to write certain things if I want to. Yeah. Okay. Yeah. So I'll be so this is I'll be talking mostly about predicate abstraction, and I've collected these slides from a few sources, and yeah, they are suitably referenced, I think. But yeah, not many of I think, yeah, perhaps none of these slides are mine, and but that's only because there are these very insightful and beautiful slides available on these topics. This is a fairly mature topic in that sense that it's been around for 2 decades, and this has created a lot of
For
interest.
20 years, I would say. I think so.
Yeah.
Predicate abstraction and the CGAR method were earlier to PDR. Okay.
Yeah.
So I think about 15 years, I would say. Yes.
Yeah. 20 I think was the right thing, as you said earlier.
Okay.
PDR, I think, is about a
10
decade
years.
older. Yeah.
10 years. Yeah.
Yeah, 10 years older or newer than this. Yeah, sorry. Okay, so yeah, and this has generated a lot of interest. In fact, this is it because the way this is done, and the kind of implications that it has, and in fact, some of these things that we are doing very recently. There also we are using predicate abstraction. Sir and I have been looking at this together, and I'll tell you some about that if time permits, and how these things are even applicable and meaningful today. So yeah, so let's start. Yeah, so this is yeah, so I'll jump straight to an example, but before that, the only thing that I would like to say is that whenever we are talking about abstraction, we are interested in reducing the size of the model. So you have been in this model checking class for so long, and you would know that the number of states available to be explored is in general a big problem in when we are trying to verify properties about systems or complex systems which have too many states. So we don't want to be looking at a large number of states because that's expensive. So we want to remove, or in some sense we want to get rid of states that are not very relevant for the property that is being analyzed right now at any given point. And this is related to the task of I think in program analysis you hear things such as slicing of a program, where you remove parts of a program which are not really impacting your property or the thing that you're trying to analyze for. Okay, so in general, there has been a lot of interest in knowing what is irrelevant and then removing the irrelevant thing, because systems are becoming complex, and this is the level of details are too many. So therefore, it will be good to know what is irrelevant so that we cannot focus on what is irrelevant, leaving us only the relevant part to focus on, which will make things tractable in general. Okay, so this is what we want to achieve by doing any abstraction for that matter. Okay, so in general we want to there are too many states, or there are too many details, and we want to remove some of these details, or we want to not talk about some of these details, and that's why we do any abstraction. Okay, but in general, it's a difficult thing, you know, because you don't know, as I said, you don't know what to remove. You don't know what is not relevant or what is relevant. So it becomes a difficult task to find out, you know, what can be removed. Okay, so this is an interesting question, and we'll see, you know, how some of these things are done, and how we can answer this question still. Okay. So we'll start with a very simple example, which will just give us the basic idea, and then I'll get to some more examples, and then we will get into more details. But let's look at this example. This example is a very simple system. It consists of these 6 states. And from some of these states, you can go to some other states, right? So you begin with this state. You know, this is the symbol of an entry state. So you start in this state, x is equal to 2, y is equal to 0. And then you can go to the state x is equal to 2, y is equal to 1. And then you will, you know, as it turns out in this transition system, you will just remain at that state. Okay, so this is what this transition system has, but it has all other 4 states. One of them is not reachable at all. And there are these 3 states at the bottom. The last 2 are reachable from the first, but the first itself is not reachable from the beginning. Okay, so this gives us some number of states. So let's look at what abstractions are, and then we will try to see, you know, why doing this makes sense for programs and properties in general. Okay, so we'll just look at what abstractions are. Okay, or what predicate abstraction is. Okay, so whenever we are doing an abstraction, as I said, when we are doing an abstraction, we are trying to get rid of some details, hopefully, you know, the irrelevant ones, but we don't know. Okay, so we'll try to get rid of some details. And here we'll try to do this with the help of predicates. Okay, so we have these 2 predicates that are going to help us. Okay, so how will they help us? Let's take a look at it. So you have these 2 predicates, x is greater than y, and the second predicate y is equal to 0. Okay, so once you have been given a bunch of predicates like this, you can, for any state, you can find out, you know, which of these 2 predicates hold, right? You can evaluate, because the state is evaluation of all the variables. For instance, you know, the state has x is equal to 2, y is equal to 0. The state has x is equal to 0, y is equal to 0. So every state is nothing but evaluation. And you can evaluate a predicate. Given evaluation, you can evaluate the truth value of this predicate. Okay, so let's try to see, you know, where all this predicate P1 holds true.
One small thing. Yeah, Ratnakar, anybody can ask questions.
Oh,
no?
okay, of course. Yeah.
That's obvious, but I mean, I just wanted to remind. So don't.
Yeah. Certainly. And, you know, I can't see the chat, or, you know, when I'm presenting, I can't see anything else. So just speak out. You can stop me anytime, and, you know, we have plenty of time, and we can cover all this. We'll not.
Yeah, I mean, I can see the chat thing. So if there is anything, anybody wants to raise hand.
Yeah, certainly.
Yeah, put it in the chat, and I will interrupt you.
Yeah. Or you can always directly interrupt me. I also perfectly acceptable. Yeah. So we're looking at these. So we have been given these 2 predicates, and we were looking at this transition system, and we wanted to see which predicates hold true where. And we can do that because a state is nothing but an evaluation of you know, concrete values of all your variables. And now you can, you know, once you have the concrete values, you can evaluate your predicate. Okay, so for instance, this one says that x has to be bigger than y. Okay, so it holds here, it holds here, it does not hold here, it does not hold here, it does not hold here. Remember that it has to be bigger than y, so being equal to y is not enough. Okay, and it holds here. Okay, so it holds in these 3 states. So I can go ahead and then write, you know, instead of this, I can write, you know, P1, and not P1, not P1, not P1, and P1. Okay, and similarly I can do for P2 also, right? P2 has to be, whenever y is equal to 0, P2 holds. When y is not 0, P2 does not hold. So these are the 3 states where y is equal to 0. So I'll say P1, P2, and here I'll say not P1, P2. Here I'll say not P2. Here also I'll say not P2. P2 and not P2. Okay. So given a bunch of predicates, this is something that we can do. Given some states, we can find out which predicates hold where. Okay. So now remember that these states can be too many, right? So you have like here you have these 6 different states. Okay. But given 2 predicates, you can only be in states where they are both true, or they're both not true, or one of them is true and the other one is not true, and so on, right? So given 2 predicates, you can only be in 4 different states. Given 1 predicate, you can only be in 2 different states. So given a predicate P, you can only be in a state where P holds, or you can be in a state where not P holds. There are not too many choices otherwise. Okay. So similarly here, we can be in one of these 4 states. So if you try to think about it, what are these 4 states? So you have P1, P2, which somehow encompasses these 2, and then you have not P1, not P2, which captures these 2 states. Okay. And then this is your 3rd state, and this is your 4th one. Okay. So these are the 4 states that you are in. Okay. So as you can see, we already came from a system that had 6 states to one that has only 4 states. Okay, which is what this is, right? And this is what I was talking about. So you have the first one has P1, P2, and it has both these states: x is equal to 2, y is equal to 0, and x is equal to 1, y is equal to 0. And then you can go, the arrows currently they represent the concrete transitions that you had earlier. Okay. So once you have done this, you can also now the question is that you have your abstract states. So these represent your abstract states. So now you must have abstract transitions. You must find out from which abstract state can you go to which other abstract states. Okay. So let's ask this question, and yeah, I'll not get into some of these details right now. Okay. So what is if we have to ask this question that from which abstract state can you go to which other abstract state, loosely speaking, what is it that you can see here? So given this the first abstract state, which is denoted by P1, P2, you can notice that, look, in the concrete, in the original one. So sometimes I refer to the original one as the concrete thing, just to contrast it with the abstraction, which is what we are trying to create. Okay. So in the original one, you could reach this state. And now this state is a part of this bigger abstract state. Okay. So we'll say that, the bigger one is reachable. Okay. So the first one is reachable because something inside that is reachable. Okay. Now, how do you go from any abstract state to any other abstract state? So if you have any state in this taking you to any state in the other abstract state, then you will have an abstract transition. For instance, this is the original one, and then you will have this, because it's possible to go from this particular state to this particular state. So therefore it's possible to go from the abstraction of this to the abstraction of this. Okay. Similarly, it's possible to go from here to here, because it's possible to go from this concrete to this concrete. Okay. So you can do that. Okay. Now, if we see, you can go from here to here, and you can go from here to here, because it's possible to go from this one in this particular abstract state to this one in the same abstract state. So therefore, there is a self loop here. Okay. So we understand these blue regions and these blue broad arrows. Okay? So we understand these things. So these are abstract states, and these are your abstract transitions.
Yeah, and I guess there's the initial state also. So if,
which is here.
Yeah, if any of these states is in that abstraction is an initial state, you will have to make that an initial state. That's how.
Okay. So now, so now let's get to the point. Why are we doing this? We are doing this because we want to verify certain properties about this transition system and so on. Okay. So let's take this property, which is P1 or not P2. Okay. Okay. So let's see. So P1 or not P2. We want to find out where all P1 or not P2 holds. Okay, so P1 or not P2 holds here because P1 holds here, P1 holds here, so P1 or not P2 holds here, and P1 or not P2 holds here because not P2 holds here. Okay, so if we take a look at this property holds in this one in the first initial state where P1 P2 hold, in the second one where P1 and not P2 hold, in some sense the fourth one where not P1 not P2 hold does not hold here. Okay, but you can see that the abstract transitions can never take you to this particular state. This is unreachable truly. Okay, so since this is unreachable, this property holds in the system because of in all the other three reachable states, you can start here, then you can go to here, you can remain here, or you can go here and you can remain here, and so on. So you can see that this is not reachable, and therefore this property holds. Okay, so this is one of the things that we could do, for instance. Okay, how to do this is a completely different exercise, and how did we land at these predicates and so on. So we're not going to worry about this right now. Okay, why who gave us these predicates? Okay, and okay, but once we are given these predicates, we realize that we can do all this, and then we can talk about properties of the system, and we can try and verify whether some property holds in this abstract transition system or not. Okay, so let's look at another property. Okay, so this property says that x has to be bigger than y. Okay, so now if you really look at if you go back to the old system, the original system that you had, you want to verify whether x has to be bigger than y or not. Remember that x is bigger than y initially. Okay, when you start, x is bigger than y, and then all you can do is you can go to this one where x is bigger than y, and you continue to remain in here. So x will always continue to be bigger than y. Okay, so there's no way that this property will not hold. Okay, so we know this from the original. Now let's go to the abstract. Okay, yeah. So we are trying to verify this property here. Remember that we don't have the yellow states, we have these blue states right now with us, and we have these broader arrows with us. Okay, so in the blue state we want to show that every state that is reachable along the broader arrows, P1 holds there. Okay, so you want to see whether this is true. P1 certainly holds in the initial state, P1 holds if you go here, but then there is a way to come here, and P1 does not hold here. Okay, so this is not so this abstraction, this abstract system does not satisfy P1. Okay, it does not satisfy the whatever by abstract system I meant the transition. Yeah, hello, is there a question? Hello.
Oh, I think so. Was in a call. I think.
No, you go. Just one minute.
Okay.
I just gotta go. You go ahead. Yeah.
Okay. Yeah. Okay. So this abstract transition system does not satisfy P1, but it's not really the case, as we saw. The original one, from wherever you could go to, which was nothing but these two states, P1 was always going to be true. Okay. So this kind of a situation can arise. Once you have gotten rid of some details, you can land into what is called this kind of a situation where you have abstracted too much. Okay, so in some sense you have abstracted too much. You have gotten rid of too many details. So therefore, you cannot figure out that this property holds. It was true for the original system, but here you have gotten rid of too many details. In particular, what is it that you have gotten rid of? You have gotten rid of the fact that, by including this particular state with this particular state in your initial, you have somehow forgotten the fact that, this was not reachable to begin with. Okay, so you cannot find out, you have forgotten it, or you cannot keep track of the fact that this is not reachable. Okay, why have you forgotten this? Because your predicates, did not allow you to distinguish between this particular state which was reachable and this particular state which was not reachable. Your predicates were not powerful enough to distinguish between these two states. They could not keep these two states separate. Okay, while we would like to keep these two states as separate. Okay, so this is the point. The point is that this is not a very good abstraction with respect to this property. It cannot. It shows that this property fails, while in the original it does not fail, and the reason really is that your predicates are unable to separate the this unreachable state from this initial state, because all predicates behave the same way in both these two states. Okay, so you have only two predicates and they behave similarly, so you cannot tell them apart. Okay, this is the problem. Okay, so with this problem, what do? We try to separate these two. How can we separate these two? We need more predicates, right? We need to characterize this in a slightly better way, such that these two can be distinguished. These two states, we need to distinguish them. Okay, so we need some distinguishing predicate. Okay, something which behaves one way on this state and in a different way on this one. Okay, this is something that we need. Okay, and this is the process of refining the abstraction. Okay, this is the process of refining this abstraction. How do we do that? We do that by finding out these predicates which can help us do this. Okay, this is the general idea behind predicate abstraction refinement. I think this is a good point to stop and see if there are any questions.
Any questions? So, I mean, I usually kind of interact with Ratnak. Yeah. So you understood the reason for abstraction, do you know, guys? Okay.
So
Verbalai?
yeah, as per my understanding, we initially try to reduce the number of states, and then we use another method to solve it. Like,
Okay.
is it
Model check on the abstracts, on the abstract system after the abstraction. Sometimes, so your predicates are fine for the property. Sometimes, yes. Okay, that is the, yes.
Correct. Yeah. So I think that's a very, it's a relevant remark. So your abstraction only takes you from this, more complex system to a slightly, smaller system. That's all. Okay. Yeah, maybe the drawing did not come out very well, but yeah, the point is that the abstraction takes you from a bigger system to a smaller system, and then the way of checking continues to be the same.
Yeah, so model checking method of the abstraction system is the same, because after all, that's also a transfer system. Yes.
Also, we are converting the property in terms of the predicates.
So
also, we will try to convert the property in terms of predicate. Here, property
that is correct. That's also an observation. Yes.
Okay.
So the properties will have to be expressed in terms of the predicates used in the abstraction as well. Yeah.
Correct. So the real reason why we convert the property into a predicate, because when we are doing this, we would like to know, because see, what we can do is we can actually only keep track of sorry. So why do we have a predicate for the property, or why do we express the property in terms of our predicates? Because we would want to specify clearly what is a bad state. So if this is your bad state, and if this itself is not very clearly expressible in your predicates, then this bad state will have certain good components or some good parts of this. So the state is not fully bad. So you want to specify the bad states. You want to specify the bad states completely. You want to say that this is you want to say that this is bad, and by this you want to mean that all of this is bad. If you land inside any of this, then you get into a bad state. Otherwise, this is not very good, because you will land here and then you'll still have to ask this question that, oh, is it bad, or did this particular point where I landed, is this, does this happen to be a good point if there are also good points inside this? Okay, so in your bad region, you don't want good points to lie around. Okay, so therefore it's important that you specify your bad properly. Okay, and that's why, and the only thing that you can specify really is in terms of these predicates. Therefore you translate your property also in terms of these predicates, and ideally you would want the predicates to fully capture what is bad. Does that
Yeah. Okay.
So I also had it out.
Yeah.
That's Amin.
So
Amin, introduce
yeah.
yourself.
So like for each property, would we like do a different abstraction like for each check?
Yeah, so it's not clear, but yeah, sometimes you may have to do an abstraction done for one property may not be very good for a different property. Okay, if it works out, it's good, but it's not it's not bound to work out.
That's right.
Yeah,
So I think the answer is
Because if you think about it, what is it really that we are doing? We are saying that there are some details which are irrelevant, and let me get rid of those details. Now the details that are irrelevant for one property are not bound to be irrelevant for a different property also, right? For two different properties, different details could be irrelevant.
Yeah. So
Okay.
like the abstraction is based on the property we want to check, right? Yeah.
I think
Yeah, I mean, in some sense, this is what you're trying to achieve. You're trying to get rid of irrelevant details.
Yeah, I think, another way to answer is yes, it has to take into account the properties. Okay, minimally the predicates will have to be able to, like Madhukar mentioned, be able to completely capture the predicate. The property that is being verified. But it may abstract, once it does that, it may abstract more things in the system itself. Okay, by throwing, as long as it is still able to capture the property completely. So it can still, the predicates can still abstract more things away from the system.
None of our predicates have temporal operators, do they?
No, these are just predicates on states. No, they are not. Well, that's an interesting question. Now, the only thing is the transition system, the transition are abstracted. Therefore, one step, a thing is there on transition relation. But answer to your question is no. So these are not abstraction over multiple steps now.
Okay.
How you do that over multiple steps? Well, I guess you could do that as well, but I don't know. No, these are not. These are only on states. Okay.
Okay.
Yeah. Okay. Any other questions?
No, sir.
Yeah. So if you have to talk about transitions over whatever predicates which have temporal operators and all, I think I of course this is answering this very loosely because I've not thought about it, but it's something like that you do in your CTL model checking anyway, right? I mean, you have all
but we haven't talked about abstractions over temporal operator. We've talked about CTL, yes, but there is, I haven't covered abstraction. Okay?
Correct. Yeah. So even if we don't talk them in terms of abstractions, what you really have is you have your formulas which are temporal formulas, and you want to find out which formulas hold where, and then if you have next X holding somewhere, then that X holds in the next state, and so on, and then you try to accumulate through a fixed point calculation
that we do. But then we still continue to work on the concrete system. Okay?
Correct.
So, but if you want to define Yeah, so that's another dimension for abstraction, is how I would think.
Correct. Yeah.
Mixing the two will not help.
Correct.
So another dimension for abstraction which may be able to consider, but then there are, but that's whole opens up a big can of worms. So what does it mean? I mean, then you abstract some states over 3 transitions, or 4 transitions. I don't know. I mean, what else to?
Correct. Yeah. So the real difficulty that will come is that you want to evaluate a predicate at some point and on some state, and you don't know whether this is true or not, because you'll have to look at the entire transition system to understand whether that predicate is true or not. So that is where the difficulty lies.
Yeah.
Okay. Yeah. Okay. So. Okay, so yeah, so that's what. So moving further, we as we saw, in this one, P1 does not hold, and therefore, but as they say, this counterexample is spurious, by which it means that this is not real, because this was not, although you can land in a state where not P1 holds, but you can only land here from this one. But this one itself was unreachable to begin with. The only reason why this got included in this bigger abstract state is because you had only these 2 predicates, and they could not tell these 2 states apart. Okay, so this is the problem. Okay, so let's look at another example where you have this is.
I think I'll make just one small point. I think what you observed, what you just now said. Okay, so there is a kind of abstraction that even in K-induction, okay, maybe that's the kind of thing. Then when you say a fixed point, see, guys, you remember that K-induction, the completion, the check for completion is done by checking if it is a predicate is K-inductive. And how is that done? You say if P holds good, for example, 2 inductive, if P holds good in the current state, and if P holds good in the next state, does P hold good after the 3rd transition? Okay. Now, if that answer is no, it doesn't mean that the property P is not violated. Okay. So in that sense, there is some kind of an abstraction indirectly that is going on there. Okay. Just because if it is not K-inductive, it doesn't mean that the property is not violated. So it is the abstraction there. It is the inductive invariant, or the fixed point that the inductive invariant is. It is not too inductive, so it's not strong enough in that sense. So these are kind of 2 different things. But there is a notion of abstraction there, in the sense that if it is violated, if the K2 inductive check fails, it means that, it doesn't mean, if it fails, it doesn't mean that the property does not hold good. It just means that your induction. I don't want to confuse. Okay, so here we are directly reducing the state space, okay, through these predicates, and in all the other things, you could say that we do consider some abstractions, but they are not like direct abstractions over the concrete system. So I don't want to, let's not, confuse those 2 things. Yeah. Okay.
Yeah. Yeah, certainly. Okay, so yeah, so let's look at another example where you have a very simple program, and we want to try to use some predicates to convert it into what is called a Boolean program, because it will have only Boolean variables. So we have 2 predicates, I is equal to 0, and the second predicate being that I is even. Okay. So we have these 2 predicates, and given this Boolean program and this given the C program and these 2 predicates, we are trying to convert this whole thing into a Boolean program, because this Boolean program will have only so many states, because a Boolean variable can take only so many values and so on. Okay, how we are getting these predicates is still not clear, and we'll answer that later. But given these predicates and given this program, this is what we can do. Okay. So instead of having these statements in the program, we'll try to see what does the transition relation look like when we talk about this in terms of these predicates or their their evaluations. Okay, so this P1 and P2 represent.
I guess, okay, sorry to
Yeah, no,
since
sorry.
I've covered it in the class. Ratnakar, your question, I think it's kind of maybe this way is relevant. Forget my K induction step. I mean, that is confusing because I have shown in the class, Ratnakar, if you observe, so you could abstract multiple steps. Okay, so for example, you could abstract the entire, I mean, the body of the transition. Here, the body of the loop is only one statement here. But if you had, say, multiple statements, you could abstract it into a single statement. Okay, and maybe you can even abstract the entire loop into something. Okay, so we have seen in the class such abstractions. Okay, so you could apply those kinds of abstractions. So now that is you could say it is multi-step. It is still not exactly in terms of formulas. I mean, the predicates don't involve temporal operators. Okay, I think Ratnakar's question was, oh, can I use predicates which have temporal operators? Now, when I'm doing abstracting multiple statements or the entire loop, I mean, if I'm abstracting over multiple statements, it is like I'm abstracting XXXX. Okay,
True.
And abstracting entire loops is almost like over until operators. Okay, because while is, oh, you keep on doing this until the termination condition holds good or something like that. Okay, so you could do that. So but so you can imagine. So I think that connection is there. Maybe Ratnakar's question can be done. So you could, the point that you mentioned, the idea can be used to abstract, but then you'll have to have a different way of refinement and how you abstract and solve. So this one is one abstraction based on one way of abstracting and based on just state predicates.
Correct. Yeah.
Let's leave it at that. Yeah.
Yeah. So just to one last thing to regarding that. So Ratnakar, so why would you want to do an abstraction using predicates with temporal operators? Is it because you want to check some temporal properties, which you can do anyway, right? I mean, even on this one, you can check the temporal properties.
Yeah, I wasn't sure. I was just asking because I assumed that I just wanted to know whether the predicates that we were dividing into were
Correct.
only propositional logic.
Correct. Yeah. So in general, if the desire is to check some the validity of an LTL formula, then you can do an abstraction even on predicates without temporal operators. I mean, for instance, if you have diamond P and box Q and so on, you can just use P and Q to do your abstraction, and you can still check your diamond
So
P
for example,
and box
after
Q.
this abstraction on the Boolean program that is shown, you can still do check temporal properties.
Yeah, sure. Okay. So now, So we're just looking at this, this example to see, what how things look when we have some programs. And so we have these two predicates P1, P2. So we have two variables corresponding to these two predicates. And what we will track through this program is how P1 and P2 are changing. That's all that we can do, and that's what we'll try to do. Okay, so I is 0 in the beginning, so from this we learn that P1 is true and P2 is true in the beginning, which is what we have here. And then we have while, and this even I is directly the predicate P2. So you have while of P2, and remember that if you have if you had P2 even, then you will not have P2 even anymore, or if you didn't have P2 even, then P2 will become even. So this is what comes from this one. This is how P2 changes. P1 changes like this. So let's see what this is. P1 says that if P1 was true, then it will be false. If P1 was not true, then you don't know. Okay, which makes sense because because all you're doing is you're incrementing I. So if I was 0, then you know that it will not be 0. But if I was not 0, then you don't know whether it will be 0 or not. It depends on the value that it had. Okay, which is what is denoted by this thing. Okay. And now you have this Boolean program, which is easier to analyze than this program. Okay, than your original C program. Okay, this is what we are doing. Okay. So this is how things are being done. So you're given a program and a bunch of predicates. This is what you can do. Okay. So there's one thing which is which is good to remember in these things is that all our abstractions or all our approximations are in some sense conservative, in the sense that they preserve every transition that was there. Now if you go back, if you look at these transitions, sorry, this one, yeah. So if you look at these thinner transitions, and if you look at the broader ones, then that the broader ones preserve all the thinner transitions. Everything that you could do in the original one, you can continue to do it in the abstract one. Okay, so this is conservative. Okay.
Yeah, one point is when the abstraction is conservative as defined, as Madhukar just now defined, it's a theorem that for all CTL, okay, is preserved. Okay, since we talked about that we could do CTL, I mean model checking with CTL operators, we had talked about, okay, CTL star, and I had kind of introduced for all CTL. Okay, for all CTL is that subset of CTL that only has a universal thing. Okay, so these kinds of conservative abstractions preserved for all CTL, not existential. Okay, so that is a side comment that I want to make. Okay, so when you do temporal on the abstraction systems, you can safely, as long as it is conservative, you can do it soundly on for all CTL and of course LTL, because it has for all things. Right.
Yeah. So yeah. So this says that this will have, in general, what this means is that you have more paths in your program than like how we saw just now, that your abstraction allows you to do more than what your original allowed you to do. Okay, so therefore whenever you prove that your abstraction actually satisfies the property, abstraction satisfies the property. Okay, and these are safety properties. So whenever your abstraction satisfies a safety property, then your original also satisfies the safety properties, because if there was any path in the original one that violated the safety property, then that there would be a corresponding path in the abstraction which violated the same safety property, and therefore you would be able to. Okay, but as we had seen earlier, it is the other direction need not hold. So your property, your safety property, maybe it may be false in the system. So whenever abstraction satisfies the original, this implies that the original satisfies. Okay, but when abstraction does not satisfy, it does not imply that the original does not satisfy, like how we had seen earlier. P1 was not the property P1 did not hold in the abstraction, but it was true in the original system. Okay, true in the original system. Okay, so this is something that we have seen just now. Okay. So this is just one thing that's important to understand. Okay, so now so let's see how are these transitions computed. So basically what do you have? You have a bunch of predicates, let's say, and you're trying to you have some basic block here, and you have some predicates like this, let's say, I is equal to 1, I is equal to 2, and even of I. So remember, what is it that we are doing? We have computed these abstract states, and now we are trying to see from which ones can we go to which other abstract state. Is this possible, is this possible, is this possible, and so on. So we are trying to compute these abstract transitions, and the way to really do that, what are the abstract states that are possible? So given these 3 predicates, there are these 8 abstract states that are possible, right? Okay, so given n predicates, there are 2 to the power n abstract states that are possible. And what is it that you can do? What can a transition look like? You can have a transition from here to here, here to here, here to here, okay, or here to here, here to here. So basically, you can have a transition between anything here on the left hand side and anything here on the right hand side. And the way to compute this is to really go on checking one by one. So you check whether it's possible to go from P1, P2, P3 to to whatever to P1 prime, P2 prime, P2. So basically you check whether it's possible to go from a state where all of them are false to a state where all of them are false again. So basically, is it possible to go from this state where all of them are false, false, false to itself? Okay, this is what we are checking. Or whether it's possible to go from a state where P1 is false and P2 and P3 are true to a state where P1 is true, P2 is false. Whether this is possible or not, it can be checked. Okay, it can be checked by giving a query to the solver with respect to any block. And I think sir was making a remark earlier that this could be a bigger block, if you will. It could be a bunch of statements, if you want it to be. So you could do a transition from the state here, and it could be I plus plus j is equal to j minus 2, I is equal to 3 times j. You could do whatever. So you could have a bigger block, and then you could find out whether it's possible to go from this particular thing to a different state by going through this basic block. Okay. So how much what is the size of should you consider a transition after every statement? Should you consider a transition after every 2 statements? Should you consider all of the body of the loop as one block, or should it be 2 different blocks? These are questions that are not clear yet, right? But no matter what is the size of your block, it will have some statements, and given a state and given a bunch of statements, you can find out whether it is possible to reach this another state or not going through this. Okay, so this question can be asked. Okay, how does this look like? This looks like a query to the solver, which is this, that so for instance, what does the first query look like? I'll just sorry. Okay, so what does the first query look like? The first query says that P1 is 0, P2 is 0, P3 is 0, which means I is not equal to 1, I is not equal to 2, and I is not even. Okay, which is what is denoted here. Okay. Okay, and then you have your basic block which says I prime is equal to I plus 1. Okay, this is in the static SSA form, static single assignment form. If you have read that, even if you have not, it's not very difficult to understand this. Okay,
I think they know the pre and post prime and non-prime variables. So that's
okay, yeah. So the primed are after the transition has happened. Okay, and now this is you're checking whether it's possible to go from here to, and once again on the target side also this has to be 0, 0, 0. So once again you have not equal to 1, not equal to 2, and bar denotes the not here. Okay, and this can be given to Z3, for instance, and Z3 can tell you whether it is possible to do or not. If Z3 tells you this is possible, then you say that, or in this case maybe it's not possible. And then you want to find out whether this is possible or not, and maybe this is possible, and so on. So this is how you can find out from which states can you go to which other states. Okay.
There exists a transition in the concrete system that will take.
Okay. Yeah. Okay. So you can compute this thing, but remember that this is not a very even with these 3 predicates and this one statement here, even with these 3 predicates and this one statement here, you have to make too many queries, as you can see, right? And you could actually go from any of this to any of this, and these are just too many queries. Okay, so this is an expensive operation. Finding an abstraction is an expensive operation. Okay. Okay, so this is what yeah. So this is so far this is what I wanted to say, and I think once again if you have any questions, I think we can stop for them right now.
You said about like feeding it to the solver, right?
Correct.
So the solver will have the initial like transition system as the input, or like
No, the solver does not have the solver does not need the initial transition system, right? So all you are trying to check is that, is it possible to go from this particular state on this transition to this particular state or not? So let's call it source. Let's call this target.
I think the confusion is because the query that you put on the right side is actually on the concrete state. Therefore, this query will be on the original transition system. Huh?
Correct.
Yeah. So I think that was your question, like correct, Paramalai, that it has to be solved on the concrete thing. It is a single step transition query on the concrete system.
Correct. So this transition has to be the concrete transition, as you can see. This is concretely written.
Yeah. So, but then the question is, I guess, extending Paramalai's question: does predicate abstraction require you to compute the Boolean abstraction? No. So you will, or does it? Do you have to pre-compute all the transitions? You will have to. You will have to do it. No? So to make the abstract, in order to make your predicate abstraction work, you will have to do the Boolean program. I mean, you have to compute the transitions.
Correct. So this transition has to be computed, and in fact, this is
it has to be computed once. Okay.
Correct. And then, as we were speaking earlier, if you remember your original example, that the first example that we had seen, it had two states. And we said that, these two states it's bad to put these two states together because this is not even reachable. This was not even reachable. And this was the initial state. And we wanted newer predicates which could separate the two. So once you add a new predicate, then again, you will have to compute this. Okay. Because then there'll be a P4 here. Okay. And then P4 prime here. So then again, this will have to be computed. And that's why this is an expensive thing. If you don't get your abstraction right, every time you're adding more predicates or you're trying to, gather more information or bring more information into your abstraction, you will have to recompute all of this, which is an expensive exercise. I mean, of course, I'm not saying that, this will have to be done in the, you have to do a brute force thing every time. I mean, there are smarter ways of doing it. Perhaps some of it you can reuse and so on. But in general, this has to be computed every time. And this is an expensive operation. This is, in fact, a bottleneck of this technique. Okay. But it is still a useful technique. Okay. Does this answer your question?
Yes. Yeah.
Sir, is there anything that you would like to add here?
No, I think this is fine. Okay, so I think the method of CGAR will be doing this lazily so that you don't need to do it. Okay, so that is one point, I guess. No? I mean, the first time, so first time you will have to do the abstraction based on some set of predicates. After that, you will be introducing new predicates as and when necessary. Okay, this fashion. So that will reduce that burden somewhat. Okay.
Correct. Yeah, sure. So we'll come to the counter example guided refinement and very soon. But yeah, so these are something that I wanted us to understand, and this is once again a repetition of these things. We are not interested in this, but we are interested in this particular example. So we'll look at one more example, and then we'll get to. In fact, we'll use this example to get to refinement of predicates. Okay, so this is some locking rule in SLIC. Some thing. So, but basically, we are interested only in the in how the control flows in this particular example. So let's try to see. So so this is the state machine. The thing that you see here is the state machine, and it has two states. It has an unlocked state and a locked state. And in some sense, what this. So what are you allowed to do in this particular thing? You are allowed to do a locking. You can do a locking step. So from an unlocked state, you can acquire the lock and go to locked state. Okay, I'm just talking about some state transition diagram, and then we will try to see we will try to see a program which does some of this, and we'll try to see whether this program is correct or not. That's what we are trying to do. But we are first understanding the state machine. Okay. So the state machine has two states, an unlocked state and a locked state. From an unlocked state, you can acquire a lock and you can go to the locked state. From the locked state, you can release the lock and you can go to the unlocked state. But if you try to release the lock from the unlocked state, then you land into error. Similarly, if you try to acquire the lock in the locked state, then you land into error. Okay. So you have, this is denoted here. You have two states, locked and unlocked. Okay. Now, how does the lock thing work? Okay. So if it is locked, then you abort. Okay. So when you're trying to lock and it is already locked, then you abort. Okay. And if you're trying to unlock and it is already unlocked, then you abort. In the other case, you mark it as locked and unlocked. So basically, just this. Okay. So this is one state machine for locking. This is some locking rule that we are trying to capture here in this state diagram. Okay, now let's look at this code here, and the question that we want to ask is that does this code obey the locking rule? Okay, so what we had seen was this locking rule here, which from an unlocked thing, if you could acquire the lock, you change state, and from the lock again, if you released, you change state to unlocked. But at any time, if you're releasing from the unlocked or acquiring in the locked, you went to error. Okay. So now we want to see, these were the functions that were acquiring the lock and releasing the lock. Okay, so this is acquire and release. Okay, and this is release again. Okay, so let's look at this particular piece of the code. So this is a do while loop. So the first thing that you do is you acquire. Okay, and then you do some computation, and then in some if condition something happens, you try to release the lock, and then you loop until this condition holds true, and then you release the lock again in the end when you come out of this loop. Okay, and what we want to ask is that does this code obey the locking rule? Okay, and so we have to find out that whether it tries to acquire a lock in the locked state. From the locked state, it tries to lock again, or from the unlocked state, it tries to unlock again. Okay, so this is what we have to find out. Okay, so if we have to find this thing out, we can say that, look, a lot of these details are not important. So let me try and get rid of these details. If I only worry about locking and unlocking, so let me only worry about locking and unlocking. No, let me just get rid of these details. Okay, so I've gotten rid of everything. Okay, so remember that I had some statements here, and I had some if condition here, and so on. So there was all this the control flow. Of course, I have retained, but all the data part I've gotten rid of. Okay, so here is the program. You see that the control flow has been retained. So you have your if thing still around, your while thing still around, and so on. Okay, but you have none of these statements that were there earlier. Okay, none of this, and this also, the condition becomes a star. This condition also becomes a star. Okay, so this is your program. It's clearly an abstracted program.
So in other words, Madhukar, so you've retained the control structure, just to emphasize, and thrown away all those statements that don't influence or impact this locking or unlocking. So you're keeping only those statements that impact the change, lock and
correct.
Yeah, that's how you.
That's what we have done. Okay.
That process is kind of manual. So yeah, I guess no. I mean, yeah, but anyway, that's what it's done.
Correct. Yeah. So I was only worried about what is whether the locking rule is being obeyed or not, which is basically worrying only about the locking and the unlocking part of it. So I can realize whether right or wrong we will only see later. But I saw that most of the other thing is irrelevant. So let me throw it out. So I'm remaining only with this particular code. Okay, so let's try to see whether the locking rule is obeyed. If the locking rule is obeyed in this one, then I know that the locking rule is obeyed in the original one, because this one this one here. If the locking rule is obeyed here, then there is no way that the locking rule will be disobeyed here. Right? It's not very difficult to see. Okay, because you could be doing some other computation, it does not matter. If the locking rule is obeyed here, the locking rule is obeyed in the original program. Okay, so let's try to see this. Okay, so what happens, you start in a state where it is unlocked, because this is where you started. If you remember, you started in the state where it was unlocked. Okay, so you start in the unlocked state, then you acquire the thing, so you change into a locked state, and then these things don't impact the thing, and suddenly so this continues locked, and then you release, so you become this becomes unlocked, and then it continues to stay that way, but then you try to release again. Okay, so this is an unlocked state, and then you're trying to release, so you land into error. Okay, so this abstraction tells you that it's possible to do an unlock from an unlocked state. Okay, so it's possible to do this. Okay, so we'll try to, so there are two possibilities, right? So the first possibility is that it's not possible actually. It's not possible actually, but but our abstraction is not good. Okay, but abstraction is not good. Okay, and the second possibility is that it's actually possible. It's actually possible to do an unlock from an unlock. Okay, so we want to find out which one of these two is the case. Okay, because if this is actually possible to do this unlock to unlock, then we are done. We know that it's possible to violate the locking rule, and we have produced one trace in which this gets violated. So if it is indeed actually possible, we are done. Okay, but if it is not possible, we'll try to do something about it. Okay, so let's try to see if it is indeed possible. Okay, so what was the counterexample trace? The counterexample trace said that, look, you went here, so you started in an unlocked state, then you went here, you acquired the lock, which is fine. Okay, but then you went here, you were in the locked state, you released it, you went to the unlocked state, and then you came out of the loop, and then you released again. Okay, so this is what your counterexample trace tells you, but this is the abstract counterexample trace. Okay, this is the abstract trace. Okay, so we want to see whether this is actually possible or not, and by actually possible, we want to see whether it is possible in the original one also or not. Okay, so let's go back to the original one and see whether it is possible to do so. Okay, so this was your this blue highlighted thing is your abstract counterexample, and right now we want to check whether it is possible to do so or not. Okay, so what happens? So you start in an unlocked state, then you acquire the thing, you lock it. Okay, and then this is something that happens, but we had abstracted this earlier, but right now we are checking whether it is possible to do it in the original one or not. So we'll keep track of this also. Okay, so this one does some, it sets some n packet old variable to what was n packets. Okay, and then there's some request, and then the request is request next, and there is a release, and this variable is incremented by 1. Okay, so what really happens is that your n packets old was this variable, and then this variable got incremented by 1, so your n packets old became 1 lesser than the than n packets, right? And then you came here, and then you exited out of the while loop. So when you come here, you realize that, look, it's not possible to exit out of the while loop at this point in time, which the abstracted one allowed you, because you had not tracked any data, so you had no way of tracking this particular condition, when it will be true, when it cannot be true, and so on. So this had been converted into a non-deterministic condition for you. But you realize here, when you're looking at the concrete, that, look, you cannot take this trace, because if you take this trace, these two will be equal, but then this will become bigger by 1, and now these two certainly will not be equal, and therefore if you come like this, you cannot exit the while loop here. Okay, so so what is it that we are doing? So remember that we had said that there are two things which are possible. One is that this is not possible in the original, but the abstraction was not good. But before coming to that, we are checking whether it is actually possible in the original. Okay. And in this case, it turns out that this is not possible in the original, right? So this is called a spurious counterexample. Okay, if it was possible, it would have been a real counterexample, and we would have been done. Okay, we would have told that this code violates the the locking property. Okay, so this is a spurious counterexample. So once we have a spurious counterexample, we need to refine our abstraction. We realize that, look, these are details which are important. We cannot get rid of all of this, certainly, because the earlier abstraction was bad. Okay, so some of these details are important. I don't know what details are important, but let's try to get some details. Okay, so we now track this predicate which says that whether these are equal or not. Okay, because this is the predicate that was we came out of this loop, and it was on not B holding true. Okay, for some reason we decided that we'll try to track this predicate to gain better control over this whole thing. Okay, so we decided to track this predicate. So let's track this predicate now. So when this is so it can start with B is equal to star, because you don't know. And then when this happens, you set B to true. And then when this happens, you because n packets got increased by 1. Okay, so if these two were actually equal earlier, then they'll certainly not be equal because one of them has increased. If these two were not equal earlier, then they will then they may or may not become equal. So therefore this is a star. We had seen a similar expression for our earlier example. Okay, so this is how. So once again we are tracking not everything, but we are tracking this Boolean predicate which tries to remember whether these two are equal or not. Okay, this is what we are trying to remember. So when these two are set to be equal to each other, we set it to true. Then upon this increment operation, we this is how this evolves, and then this condition is represented by not B. Okay, so now this becomes our new abstraction. Okay, so this is a so we had an original we had the original program P, from where we got our first abstraction, which was which was unsafe because we got a counterexample. Okay, so then we added this predicate B, and now we have got our second abstraction, which is this. Okay, and now in this one we can check once again whether it's possible to reach the error or not. Okay, and you can do this exercise. I think at this point it is not possible to, yeah, so you can do this exercise, but you can check that it is not possible to do. It is not possible to so if you do a model checking of this program with respect to your locking property, you will see that it's not.
Hello? Oh, maybe he dropped off. You guys are there, no?
Yes.
Okay, so I think Madhukar must have had a power cut. Okay, let me call him. Yes, Madhukar. Hello? Oh, okay. Yeah.
I have to be made a co-host again, or oh no, I'm already a co-host.
I think
Yeah, I'm already a co-host. Can you see my screen?
beginning to. Yes. Yeah, now we can.
Okay. Will the recording have to be started again, or is it recording?
No, because the session has
Okay.
not.
Okay. Yeah, sure. Yeah. I'm sorry about that. So I'm not sure, where you had lost me.
No, you said that how you I mean, yeah. So you were saying that
Correct.
That you'll
Yeah, you said like the A2 will work. like it
Correct,
won't be
correct, correct. I
informed.
said that, you can check that A2 will work, but yeah, so it's possible to check that, A2 will work. And like how you would model check, your program with respect to, this is still much better than, checking your original program. If you see it, original program had a lot of other details which you are not keeping track of. And you're just simply, you have a very simple program where there's a Boolean variable, which it's true here. And then, it has this, there's this conditional assignment expression. And then there is a loop where you have the negation of this thing as the condition. Okay. So you can see that, in this one, it's not possible to reach. It's not possible to do a lock on a lock or an unlock on an unlock. Okay. So this is this process of finding out that you got a counterexample here, and you realize that this counterexample was actually spurious, and then you added a predicate, okay, which is the refinement part of it. So you added a predicate and then you refined the whole thing, and this refinement worked. Okay, so right now you can check this, and you can you can assure yourself that this is a safe thing. And at this level, if it is safe, then still, because this is a conservative abstraction, as this is one of the important properties. Our abstractions are going to be conservative always. We will always preserve paths so that, whenever we say that a safety property holds, it will continue to hold in the original one. Okay. So we have seen through some 2 or 3 examples that it's possible to use some predicates to abstract away some information. Okay, but what are good predicates? How to do this is not, how to find good predicates is not clear. The other question which is not clear is, when we land at a spurious counterexample trace, we need more predicates. Okay, so we need additional predicates to get a better abstraction, something that works. I mean, this one happens to work by just adding 1 predicate. This may go on for a while, and your A2, and then you get your A3 by adding some 2 more predicates, and then B1, B2, B3. This can go on for a while, and maybe your A5 is the one that helps you prove this thing. Okay, so after some levels of refinement, you may be able to establish the property. Okay, so this is what is important, right? Okay, so now there are okay, so there is yeah. Is there a question?
Yeah. How did we came to the conclusion that the previous abstraction is not a good one?
The previous abstraction is not a good one because the previous abstraction had this counter example. This was possible to reach in the abstraction, but when we tried to do the same thing in the original one, we were not allowed to do this. Therefore, the original abstraction was not safe.
Okay. So there will not be a case like a property which was not holding in the original will hold in the.
No, that is not possible. That's what he explained. In conservative,
Okay.
If it's in varying
because abstractions are conservative. Yeah.
Okay. My internet went off. That's why no problem.
Okay. So this is the reason. Yeah. So we are always, so whenever we are checking safety properties, we are, it will never be the case that a safety property is false. It does not hold in the abstraction, but holds in the, it does not hold in the original, but holds in the abstraction, because the abstraction will always have more behaviors. So we are only going to add behaviors. By not keeping track of, certain things, we are allowing more behaviors. Okay. So it will never be that case. Okay. So we know that, there are, we can land into abstractions which are not good enough because they will have spurious counterexamples. So therefore we need to refine our abstractions, and that we'll do with the help of additional predicates. Okay. So the process of finding this, these, how to find these predicates is a question. Okay. And, Sir has been talking about, CGAR, and I'm sure, you would have heard this term maybe a few times. Sir would have talked about CGAR.
No, I have
maybe
not.
Okay. So CGAR, yeah. So, but yeah, he certainly mentioned this. So CGAR is a term we used to used for this kind of a refinement. So it's called counter example. The C stands for counter example, G is for guided, And this is for abstraction refinement. So you want to do a counterexample guided abstraction refinement. So what you're doing when you're going from A1 to A2, you're actually refining the abstraction. Okay. So it's a coarse abstraction to begin with, but then you add some more predicates. Every additional predicate will track some more things through the program. It'll carry some more information, or it will make some more information available at different program points. And therefore, you're having a more refined abstraction. It is still an abstraction, but a more refined one. Okay. But if you're doing it with respect to, once you get a counterexample, so remember that, here we had a counterexample, and when we tried to run this counterexample in the original program, we found out that this is spurious. So if you take such spurious counterexamples, and you using these counterexamples, if you find out the predicates that are to be added, then this is called a counterexample guided abstraction refinement. In this case, this is a counterexample guided predicate abstraction refinement. Okay, so this is the point here, right? That you need to really refine your abstraction, and what you have to use is the counterexample. Okay, so I'll give you some ways in which this can be done. Very quickly and very briefly, I'll tell you a few things that you can do to get these predicates. Okay. And once we answer this question, that how you can do a refinement, we can answer this other question also, right? Because in some of these abstractions, you saw that I started with this predicate P1, P2. Nobody told me these predicates. How did I get to these predicates? How did I realize that P1 and P2 are nice predicates to begin with? Okay. So once we are able to do a counterexample guided predicate refinement, this question of this original set of predicates to start with is not very important then. Once we are able to add predicates and do a refinement, I could start with anything. I could maybe start with the property as a predicate, or a bunch of predicates that I see in the program itself. For instance, here I saw that this is a nice equality, so I'll start with this as a predicate, or I could start with any predicate. Okay, I could start with the property as the predicate. I could start with if there is some condition here, then maybe this condition I can start as a predicate. If you think about it, this is what is a predicate here also. I mean, not of the predicate or the predicates, the same thing. Okay, so you can start with any predicate. Okay, that does not really matter. I mean, of course, if you have a not very useful predicate, it's not very good, but it's okay. It's okay to start with some predicate.
Yes, I guess what you mean is you can start with a very coarse predicate. Okay.
Correct. Yeah. What I mean is, yeah.
Yes, and then do refinement. I mean, refine it as you go along. Yeah.
Correct. Yeah. So you can start with, you can pretty much track as little as possible, as you can get rid of pretty much everything, most of the details, all of the details, except that you're just perhaps tracking the property or something which lets you decide what is good and what is bad and so on. Okay, so you can do this. So this question of which ones to start with, we will not worry too much about it, because we have a way to do a counterexample guided refinement. Okay, so I'll have a way to find and add predicates, so we'll not worry too much about which predicates to start with. We'll just start with whatever. Okay, so now let's see what are the ways in which this can be done. So I'll tell you there are 3 ways. Of course, I'm sure it's possible to do it in a number of ways, but I'll tell you 3 ways in which this can be done. Okay, so remember your example here, right? So if you remember, this is your abstract state, and as you notice, it allows you to, it tells you that you can go from here to here, which was leading to the spurious counterexample, right? This particular transition was leading to the spurious counterexample, because this abstraction told you that it's possible to reach here, because these 2 states cannot be distinguished. Since this is initial, this also falls in the initial abstract state, and then you can do this. But the point is that this is the true initial. This first one was the true initial, and the transition to go from this state to this state was actually happening through this, which was not even the true initial. Okay, so you need to separate these 2. Okay, so what is one way of separating these 2? Okay, what are the things that you know? Okay, so you know that, look, it should not be possible to go from here to here, right? You want to separate this into two states such that your initial falls in one of those things. You want to separate this, so you have your p1 p2, okay, which is not enough. You want a p3, okay, so you want a p3 to describe this, okay. And what are the constraints that you have on your p3? Your p1 p2 p3, they will describe this particular thing, this half of this. So what will this state be split into? Every time you have added a predicate, you will have, earlier this was p1 p2, now there'll be two parts to this. There'll be p1 and p2 and p3 part, and then there'll be p1 and p2 and not p3 part of it, right? So every time you add a predicate, you split your states into two. Okay, everything splits into, there are twice the number of states. Okay, so everything becomes twice. Okay, so there is this particular thing where this this point sits, and what is the spuriousness? You realize that wrongly you were thinking, you landed into this particular state in the initial, and then you thought that it's possible to go from here to here. Okay, while it was not possible to go from here to here. It was possible to go from here to here, not from here to here. And it was not possible to start in this state. It was possible to start only in this state. So you need to split these two. Okay, and this is what is done with the help of a predicate. Okay, so every time you add a predicate, it splits every state into two. It will split this one also into two parts, this one also into two parts, this one also into two parts. May not be like this, they may all be on the same side, but it will split it into two parts. Every region will be split into two parts, one where the newly added predicate is true, and the other where the newly added predicate is false. Okay, so now you can use a constraint solver to give you this new predicate. Okay, what are the constraints that you tell this to a constraint solver? So you tell your constraint solver that, look, I'm looking for this new predicate p3. Okay, in fact, I've written down this constraints somewhere here so that we can take a look at it more easily. I'm not sure whether I have them here. Yeah, okay, I have them here. Okay, can you see my sir, can you see the text file?
Yes.
Okay, yeah, okay. So you had this p1 p2, and now you have added a p3. So now you have two different states. So you have p1 p2 p3, and you have p1 p2 not p3. Okay, now remember that you have to split this into two parts. You have to separate this one from this one. Okay, so what are we saying? We are saying that the part where so I'm assuming that this p3 is the one where this one belongs to, the first one belongs to. It doesn't matter, it could be not p3, but the predicates are allowed to have negation, so you don't have to worry about that. Okay, so the first thing that we have to say is that, look, the first concrete state, the initial state, must belong to the part where p1 holds and p2 holds and p3 holds. Okay, so this is something that you tell your constraint solver that I'm looking for you tell your constraint solver that find me a p3 such that the first one belongs to that. This state, this initial state, x is equal to 2, y is equal to 0, belongs to p1 p2 p3. Okay, and from this p1 p2 p3 part, from this particular part, I should not be able to go here. Okay, from this other part I can continue to go here, which is how it was there in the original one also, right? So from the other one, from the p1 p2 not p3 thing, you can continue to go here. Okay, but from the p1 p2 p3 you cannot go to, and remember that as I was saying, this not p2 not p1 not p2 thing will also be split into two things, not p1 not p2 p3 and not p1 not p2 not p3. Okay, and you don't want to go to any of these. Okay, so you from p1 p2 p3, which is your top part, you don't want to go to this, and you don't even want to go to this. Okay, so now you can give these constraints to a constraint solver, and the constraint solver can find you a predicate. Okay, In particular, there are these synthesizers or syntax guided synthesis solvers, or even constraint solvers. This is same as the problem of what is called the problem of logical abduction. Okay, abduction is nothing. Abduction says that if you have so let's say if you have a P which should imply Q, but P is not implying Q, what is it that has to be added here such that Q can be implied? Okay, this is the problem of logical abduction. Okay, in some sense, these problems are related. You can read about this problem of logical abduction, and this problem of logical abduction can be solved using Z3, for instance. Okay, or this can be solved using what are called Seiger's solvers, for instance. Okay, Seiger's stands for syntax guided synthesis. Okay, so basically this task of finding a predicate, you can give this task to a solver. Okay, there are solvers for this, right? Seiger's solvers, and Z3 is a solver, as you know. Okay, so the task of finding this thing, you can give this to the constraint solver itself. What is it that you do? You really use the counter example. So of course this has become a mess, but this, what was really happening is that so you had your your counter example said that it's possible to start here and then it is possible to go here. This was your counter example, which was spurious because you can land here but you can never jump. This jump which was happening inside this abstract state cannot be allowed. Okay, so therefore now you have split this abstract state into two parts. Okay, such that this jump is not implicit. Okay, explicitly if there is a transition, then there can be a jump, but this implicit jump you have blocked by separating the two. Okay, so you can really use your counter example to get these constraints. Okay, these are the constraints that we have derived from our counter example. We have said that, look, the first one, the top state should belong to the part where the new predicate is true. And then from one of the parts, you should not be able to go to, any of these, the other states. Okay. So this is one way of doing a counterexample guided predicate abstraction refinement. Okay. Very quickly, I'll just take 2 minutes and I'll tell you one more way of doing it. So I've told you a way to do it using this problem of logical abduction. Okay, you can also do it by what is called a syntax guided synthesis thing, and if you're interested in any of this, you can always speak to me about, or you can ask sir, and you can write to any of us and we'll tell you. But these are two different ways. And the third thing that you can do is you can actually use interpolants. Okay, remember, what are interpolants? Interpolants tell you that, if a bunch of things are, if two things are inconsistent, if A and B are inconsistent, if A and B is unsat, okay, then you have interpolants as A prime, such that, A implies A prime and A prime is still inconsistent with B. Okay. So you have and then for a sequence of things which are inconsistent, you can have interpolants at every between everything. So now you can take any counterexample trace that is spurious. For instance, if you go to your if you go here, you can actually collect these statements, this S1, S2, or it could be a block of statements S3, S4, S5. Okay, and really, if any trace is not feasible, then if you collect these statements S1, S2, S3, then you will see that S1 and S2 and S3 and S4 all the way up to error, this is unsat. Okay, so every time there is a formula that is unsat, you can get interpolants. Okay, interpolants from the infeasibility proof or from the unsat proof. Okay, so the solvers, whenever they tell you that it is unsat, the solvers can also be queried for an unsat proof. Okay, and these unsat proofs are basically things that are true here and here and here and here at all these intermediate points. Okay, so now if you look at these things which are true at these intermediate points, they will look like small lemmas. Okay, A is equal to 2b, A is equal to 3b plus c, A is equal to 4b minus d, whatever. Some small lemmas which are true at intermediate points. You could use these as your predicates. Okay. So these are some 2 or 3 things that you can use as your predicate when you're doing a counterexample guided predicate refinement. Of course, we have just scratched the surface. As I said, this is a very mature field, and there's a lot of interest in this. In doing an abstraction in general is a very powerful tool.
One thing that I would add is, yes, this is a very powerful framework. Okay, but it is still there is a lot of research that is still going on. There are systems, okay, that are amazingly successful, like one that Madhukar had mentioned in the earlier slide, which is SLAM. Okay, SLAM. What is that? The tool that you had mentioned. No? So,
yeah.
SLAM, which is a Microsoft tool that is used inside Microsoft. There is one way of abstracting, but there are new ways of doing these things, and there is a lot of unexplored open questions in this field. I mean, he pointed out Cygus and how do you do abduction and so on. So there's plenty scope for research, and still how you do that. So while the framework is mature and the idea is mature, how you do all these refinement and abstraction to various things. And there's a lot of unexplored territory.
Correct. Yeah. Certainly, because so the last remark really is that because if you think about it, it's a very difficult question, right? I mean, what is relevant to a property? It's a very difficult question to ask and answer. If you're trying to verify a property in a system, which part of the system is relevant? This is an extremely difficult question to answer. We can only guess that, this part, some parts, of course, we can guess with more confidence, and that those are the kind of things that we retain in our original abstraction. But for a lot of other things, we can only hope that this is something that is useful, and this is something that is not useful. In general, asking the question of relevance, what parts of the system are relevant to a particular thing, is a very difficult thing, and that's why there is
as difficult as your model checking problem itself. Okay, to do it conservatively and approximately, you can do, and that's where a lot of the research lies. So you can do it, but precisely doing it is as difficult as model checking.
Yeah. So and this continues to be of interest. Even today, a lot of people try to find out, what is relevant. When we are trying to do a model checking, when you're trying to verify certain properties of some programs, what is relevant? Because the systems are so complex that you just cannot hope to to have all of it into your picture. So you must get rid of some of it, and this continues to be an important thing. And it will continue to be important, even in foreseeable future. So this is an interesting direction in general. Yeah, I'm sorry I could not cover a lot of it today, but I'm always available for discussions or for anything you can. I think at the end of it, I think I have a slide where so you can always write to me.
That's a good point to end. Any questions?
In the example that we did see, we did end up with more states than we originally started, right? 3 predicates means 8 states.
Yeah. So of course, in general, but So in general, it's not. So in that case, that happened to be a very simple program, and there was a need to add a third predicate. But you saw a couple of other examples where we had much lesser. Right, so that is not a program where you will do, the first one is not something, at least for that property, it is not something where you will do predicate abstraction.
Yeah, but
I just wanted to.
Ratnakar, so I mean, you were comparing. I mean, that was a simple example, so you're right. But you were comparing because you already got. See, the starting point there were integers. Okay, so potential states are very large there, okay, with integers, even if you assume they are only finite precision integers. Now, Madhukar actually drew the example, he drew the entire thing, and therefore you knew what was reachable and what was not reachable. So you already had a partition in mind, okay? And somehow, a priori, you knew that, oh, this was reachable, that is not reachable, and he only showed only those things. Huh? But yeah, so but you would not know that, right from the start. Huh? So I could say that the potential state there are as big as the integers, the cross product of all those x and y.
Right.
Only after you propose a set of predicates will it even be 8.
No, the reason I asked is I wanted to know does the process have any sort of termination thing? We keep on refining until.
That's a good point. I think that's a question that I also had, Madhukar. Maybe you want to take that. So when does this process terminate? Okay, so when all the counter examples are exhausted. Okay, so
correct. So yeah, so if you think in terms of the abstraction refinement, so the abstraction, when you're abstracting, you are adding more paths into the system, into your system, and when you're refining, you are getting rid of some of these additional paths that you had added. So when you have refined sufficiently such that your original program and the abstract program have exactly as many paths as each other, then you have reached the original program back. And that's when you cannot hope to. So basically, what is the hope behind these abstractions? The hope is that you can get rid of some of the details and you can still verify the property. What can happen is that it might actually be true that you can get rid of some of the details and verify the property. You don't know how many details, so you start with getting rid of a lot of details and then you add more details. But then in the end, you would have added back all the details, and now you get back your program. In that case, it is not possible to get rid of any of these details and still prove the property. You can prove the property on the original one, but it's not possible to remove any of this. And because the moment you remove any of this, you get spurious counterexamples. What do? So you have to add back the detail, right? Does this answer your question?
Yeah, I think I mean, I would add Ratnakar. So I mean, I have something to add. No. So theoretically, answer to your question is, it will terminate when all the counterexamples are eliminated. Okay, and there are only finitely many counterexamples if it is a finite state system. The question is, so if you're only eliminating one counterexample at a time,
correct,
but the abduction process, like he talked about interpolance and abduction, so there you would still, you're not directly going from one predicate to as many predicates as you require to distinguish all the states. You always go one kind of a time. So there you will have to do some clever things. These interpolants, etc., will give you as much, I'm not eliminating only one counterexample, but rather I will introduce just enough predicates to maybe the predicates that introduce may eliminate more counterexamples than what the specific counterexample that you used to refine it. Okay. Now, there is also this thing of generalizing those counterexamples. You're already working on, you remember that? This is the counterexample to induction in PDR that you're working on, is also eliminating one counterexample at a time. There is a refinement that is going on there as well. What are you refining there? You're refining the candidate invariant, okay? Which might be, 2 cores. So you could use generalization and some such an interpolant, doing it through interpolances, doing it that way. So I'm providing 2 answers. One is the theoretical answer as to why it should terminate. That Madhukar also answered that, it'll terminate only when all the counterexamples are eliminated. But from a practical standpoint of view, that may not be that good an answer. I mean, a satisfactory an answer, because the number of refinement steps would become too large. Yeah. So you'll have to use some clever things to eliminate multiple counterexamples and do this, discover predicates in a clever way. while you refine.
True, certainly, sir. Yes.
That's why the cleverness and the how you do it lies, so that the number of refinement steps will not degenerate into eliminating one counterexample, spurious counterexample at a time. I mean, to have another comparison, see, there are few things that are there in PDR that you're doing that are common to here. See, when you eliminate counterexample to try to eliminate counterexample to induction, you try to check the blocking phase is actually checking whether the counterexample is reachable. Counterexample to induction is really reachable from the initial state. That is like checking if it is spurious or not. Okay. So the way that Madhukar said that it is spurious, I mean, he says that if there is, if that trace that he gets here, he's getting traces. There, you're generating the trace by computing predecessors and so on, all the way to the initial state. Okay, so there is some similarity there in the elimination. I don't know if you guys saw the analogy. Did you, or maybe did you see the analogy? I mean,
not exactly, but
okay, then never mind. Okay, no, the trace is, if he gets a trace, then the checking of the trace whether it is feasible on the concrete thing is exactly saying, okay, if it is reachable from the initial state or not. Anyway, so if it doesn't,
yeah, but in some sense it is true that in both these things you're trying to have an over approximation which you try to refine by gaining more information.
That's correct.
So in that sense, this
approximation is for the transition system. There in PDR, the over approximation is for the candidate inductive invariant. Okay.
Yeah.
What you're refining in PDR is, let me see if this over approximation that I have is an invariant. Okay. Is a strong enough invariant. And if it's not inductive invariant, then I try to refine it. Okay. So that's that refinement part is there. But it is in a different context. So if it is not, I mean, I was hoping that it might add something, but if it is confusing, then forget it. Yeah. But did that answer your question specifically about when the refinements?
Yeah, I got that one.
Yeah. Any other questions? Okay.
Yeah.
Thanks.
I'm sorry I extended beyond 5 and yeah.
No, I have kept 5:15 as the thing. So we went beyond that, but that's okay. So since the last day of class, it's fine. So let's, thank you very much, Madhukar. So let's all thank
you
for giving this brief introduction.
Thank you.
And I mean, I'll communicate with you regarding the written part for the final project, which I'm almost ready. I will upload something, and the other things regarding your tutorial with Diganta for PDR, and if there is any interest in discussing automata-based verification versus things. So Ratnakar, I mean, Madhukar, he had a question for which I don't have a complete answer. I'm still trying to make notes to see how I could do. So, of course, there is a lot of automata-based verifications. If I can spend about 5 minutes, yeah.
True.
I mean, we don't want to extend the discussion here. I mean, I'm just going to explain what the question that I'm trying to do. So there is a lot of, Bookie automaton. There is all kinds of automata-based verification. Now, all of them, they will stop at, I mean, specifically for LTL, the automata, I mean, LTL model checking is reduced to the problem of checking emptiness. Okay. Emptiness, the cross product. okay, of I mean intersection of two automata. One is the specification or the negation of the specification automata. I mean, as opposed to that, we deal directly with transition systems, their logical representation, and actual computing predecessors and image computation and things like that and so on.
True.
So his question was, correct me if I'm wrong, so what is the, in practice, it seems like symbolic model checking, the way that we define using, which directly uses logic, is the way things are implemented, and most good performing tools are like, based on that. So, but there are, automata can be used as a general theoretical framework for analyzing these problems. But not many directly implement it like that, okay? Except maybe the ultimate atomizer, okay, which does.
Correct. True.
Right? So I think the question was, is automata, what is the difference, okay? I mean, are they just theory, or are they also, done in practice for implementation? Is that correct, Ratnakar? Have I paraphrased your question?
Yeah, I think so. I wanted to understand how automata theoretic methods were related to to the tools you use in practice, or if they are related at all.
Correct, certainly. So yeah, so I think sir remarked a very important thing about this ultimate atomizer. So I don't know whether you have looked at this technique in particular or not, but they have a very nice paper which is called software model checking for people who love automata. And in that one, about
okay, you are breaking up, Madhukar. So I think maybe what you can do is, if you do have a class, I don't know if Madhukar is hearing or not. If we do decide to have a class with general discussion on this topic, I'll make notes, and I can invite Madhukar also. And
yeah, certainly. I'm not sure if I'm audible.
Yeah, I mean, you're breaking up. You're audible now. So since it is late, what I had said was, rather than kind of extending the discussion today, everybody is a bit tired. So we may decide to have an extra session during examination,
certainly,
based on the interest,
to
have these kinds of this question along with some general questions about model checking.
Correct. Yeah, we can look at some, certainly we can look at some higher level insights and some more philosophical questions. If there is interest.
And if it is there, I will invite you. You're more than welcome to attend, and then we can talk about this and other questions that they have, and there may be some research topics and so on. Yeah.
Certainly. I'll also benefit greatly from such discussion. Yeah, so please do invite me, and I'll be happy to be a part of this.
Yeah.
I'll try to answer whatever I can, and how I look at things, and I'll gain from how you look at things and so on. So I think it can be a very interesting thing. I'm certainly open to this and looking forward. Hello.
Yeah. So I mean, I'm yeah. Okay. So I will let you know about that. Yeah.
Yeah, certainly.
So thank you very much.
Thanks a lot, sir.
Class, I enjoyed. This is the last class for this session, and I hope you enjoyed the course. And of course, still there are a couple of more lectures and things that you have to do. You will get feedback for the thing. Please do fill out and then see what could be done better, what you enjoyed, what could be done better. Please give your feedback, and
including if you have any feedback for today's thing, you can tell
I'm
it to
sure that will
Sharon.
be part of the lectures. That's part of your course lecture.
Yeah.
Yeah. So directly on that thing too, and I think you should do that. I mean, a lot of times I never get any feedback, okay, from the people. I mean, there's empty feedback, okay, a lot of times. So so please feel free to give the feedback. Yeah, that should be useful. Okay.